I already showed up on time. That's why. Okay. So, good afternoon and welcome everyone. So, we have today our robotics platform webinar jointly organized by SAPS RDS and Quanzer, our partner Quanzer. My name is Ralph Saab. I am the VP and the co-founder of SAPS RDS, and I have more than 20 years experience in the research and education consultancy in the MENA and Gulf territory. And I will be your moderator today for this event. SAPS RDS is a 2-year-old company, yet we are gathering a background cumulative experience of over 50 years of engineering consultancy and a long-term partnership history with the research, innovation, market specialists, and experts. We pride ourselves in a value-added proposition into our application challenges, while we're reinvesting in the local market via supporting the students' project. We help enabling the bridging of the local industry grand challenges into the domain expert in line with the Vision 2030, especially the localization of the know-how and domiciliation of the knowledge, توطين المعرفة. Our team services multiple segments in the education, the research acceleration, Industry 4.0, prognostics. As well, we service the aerospace and defense, the 5G, power, technology transfer via such high-end training and technology transfer, training of the trainers as well, business coaching of SMEs, startups, and for sure, our widely covered topic of the day, which is the robotic platform. We at SAPS RDS, we partner with very well reputable world leaders in the research industry and business consulting, companies such as Quanzer, who are present with us today, NI, known as National Instruments, PTC, CB Technology, Allied Reliability, Bitlessman, and many others. We have already established several success stories at several giants of the local market, and we are as well eager to continue being part of their successful projects. SAPS RDS is in perfect harmony with the NIDLib guideline, in line with the Vision 2030 of the Kingdom and Crown Prince Mr. Mohammed bin Salman guidelines to enable the success of the Vision 2030, with the main focus on its 4 pillars: the industry, the mining, the energy, and the logistics. And one important sub-pillar, which is the localization of the know-how and the manufacturing industry. SAPS RDS as well is the success of your initiative doesn't occur without focusing on the biggest capital and the biggest value in here, which is the human assets and the human resource value, via the continuous training program and the technology transfer that we are doing via our specialized application engineering certified engineer from our company. SAPS RDS is looking forward to collaborate with you and to be part of the vision and our region development and success. We always thrive to learn more about your challenges during this webinar, so please feel free to type your questions or comment in the chat box in order to address them at the end. Also, I would like to remind you that this webinar is recorded, so please mute your mics so that the presentation runs smoothly. As of now, I would like to introduce our speaker from Quanzer, my colleague Tuvishan. Mr. Tuvishan Rajalusingham is the Global Digital Product Specialist at Quanzer Incorporation. Quanzer is a real-time control and mechatronics solution for education and research. And the Quanzer is specialized in mechatronics solution for education and research. Tuvichans develop regional partnership with universities and distributors from across the globe. We might also have some more colleagues from Quanser joining up on demand, and in case the questions that you're gonna be asking are required, we might have Mr. Isa Al-Badawi and Mr. Murtada and Mr. Hernando. Isa Al-Badawi is the channel partner manager at Quanser, responsible for our region, and he is also responsible for developing the regional partnership with universities and partners in the APAC and the Gulf region for Quanser. Mr. Murtada Bora, he's the R&D engineer with the academic application team. He is the academic lead for the Q arm and used to be the application lead for the self-driving car research studio. He holds a master's degree from the University of Toronto in robotics and space mechatronics. And at Quanser, he is specialized in the software architecture for autonomous and unmanned vehicle. Mr. Hernando is the mechanical engineer with extensive experience in the control systems, mechatronics, and robotics. He had worked with Quanser for over 12 years. Hernando works closely with end-user business partners worldwide, providing them with assistance, training, and support. So thank you all for joining. Mr. Tuvichan, the floor is yours.
Thank you very much, Ralph. So when we start talking about research platforms for robotics, no better place than to come to Quanser. And I'm hoping you guys are able to see my screen now. Effectively, what I'd love to walk you through today is a path in terms of how researchers and professors are currently utilizing our solutions for both their teaching and research efforts. But before we begin, for those who may not know who Quanser is, I want to give you a quick background. Quanser is an academic company. We've been in academia for over 30 years now, and our name is actually an amalgamation of question plus answer. And that's where we get our roots. Our founder was a professor himself who taught at the University of British Columbia, and he strived to really put the power back into the students' hands so that they were able to explore in real time through the use of physical systems. So with regards to Quanser, we have over 80 solutions in varying different disciplines across all streams of engineering. We have over 3,000 research papers that have been published on our solutions, and we're partnered with over 2,500 academic institutions globally. So we love to say every innovation or research endeavor starts on a Quanser solution. But let's imagine some of the possibilities, especially when you're talking about robotics and manipulation. There's a variety of different solutions and paths when you're exploring the avenues. Sorry, let me just have some of these videos going. Perfect. So on the top left, what you should be seeing is a 6 degree of freedom robotic manipulator called the Denso. It's being operated through a Tele operation mode, meaning there's a haptic device, a 6 degree of freedom haptic device, that is controlling the actual Denso arm. On the right, you're seeing a hexapod or a parallel manipulator. And in this example, because Quanser solutions are open architecture, meaning you can access the hardware through MATLAB Simulink, LabVIEW, C++, in certain cases Python and ROS, it really bodes well for creativity and innovation. In the top right, you have an individual sitting on top of the hexapod, and the simulation is actually driving on the surface of the moon, or it's simulating as if that person is driving on the surface of the moon. Bottom left, we have a indexer, or again, a teleoperation example that's being controlled remotely. And to the right, we have a biomedical application being developed for training of surgeons. So as we explore, we have a variety of solutions at Quanser perfectly tailored for research and teaching efforts. Everything's touching on dynamics and controls to manipulation. And really, when you break down some of these large industry trends, such as multi-agent systems, haptics, teleoperation, cobotics, IoT, Industry 4.0, or cyber-physical systems, Quanser is looking to future-proof our technology by developing solutions that are accessible, turnkey, but ultimately still providing the resources for exploration. So what I mean by that is these solutions, 90% of them come with instructor and student courseware, along with our pre-developed toolbox that adds on to MATLAB Simulink called Quark. And I'll delve in a little bit deeper in terms of what that looks like. But to touch on our two heaviest research solutions, the Denso robotic manipulator. So it's an open architecture system, again, 6 degrees of freedom, and it's controlled through Quark, which is our Quanser rapid control prototyping software. Effectively, this Denso robot communicates with the control module or via the Denso cable, but the controller is running on the actual PC, which sends signals to the Denso control module. And this is all done through TCP/IP. So there's actually an Ethernet card in the PC, and effectively the I/O rate between the host PC and the controller is about 2 to 5 milliseconds, or 2 to 4, which includes the communication delay plus controller processing time that's required to manipulate the actual arm. Now, let's add one more layer of complexity. When you have an operation of or teleoperation using a haptics device, being open architecture, we leverage a variety of different data acquisition devices. These can be purpose-built through Quanser or through some of our strategic partners like National Instruments that have industrial-grade data acquisition devices developed open for your exploration. And what this really does for you is allows you to create a network of systems that are communicating with one another and rapidly explore through your research efforts. And one final point to mention as well is it does come with a force torque sensor, allowing you to additionally add one more layer of complexity for your efforts. Now, I did touch on Quark, which is our rapid control prototyping software. This is effectively what allows you as an end user to get real-time control capabilities and access at the lowest level in terms of the inputs and outputs. Effectively, the way you can control any Quanser system and this architecture that we've built our hardware and software on is through this platform. What we like to say is there's 3 blocks that you need to be aware of, which is the read block, the write block, and a hardware-in-the-loop initialization block. With these 3 blocks, and we'll get into a bit later in terms of how that could help in both teaching and research, these effectively allow you to have a great positive Quanser experience and allow you to control any piece of hardware from Quanser. So to jump into specific case studies, I'd like to show you some examples of how some customers have actually explored this especially on an industrial level. But to cover some basis, effectively, it's a 6-axis manipulator. The reach is about 432 millimeters, and the max payload capacity on this is about 2.5 kg. So we are on the smaller end of the industrial scale. We're not dealing with hydraulics, but the benefit to this is you're now able to leverage solutions that are networked, and they're perfect for a research lab setting. You can explore utilizing devices like this, the haptic system. You can use them as standalone tabletop mechanisms or parallel manipulators. And the best part is the aim is to give you a connected, holistic system. So when we jump into our haptic solutions that pair well with our robotic manipulators, again, 6 degrees of freedoms with 6 encoders. It's a parallel mechanism allowing you to measure the X, Y, and Z axis. So effectively your roll, pitch, and yaw. As well, you can actuate in your X, Y, and Z along with the roll and pitch. So 6 axes using 6 motors. It comes with a large workspace, so I'm going to demonstrate exactly what that looks like. Effectively, these are all high-performance motors, and it's based on a capstan design, meaning it's all high industrial grade. It's capable of high forces at the end effector, and it reduces the perceived inertia. So the parallel design along with the counterweights really make for a strong, robust system. And once again, being true Quanser fashion, It's open architecture and turnkey, ready to operate. So we had a Dean's Council, so GEDC, Global Engineering Dean's Council, where they had come to Niagara here in Canada, and we were able to leverage this teleoperation system, and we networked the systems to create a game. Effectively, on the teaching front, we were able to rig the system to have a simulated environment where you're using the foot pedal as well as the haptics device to work through a simulated environment. And you would effectively have to interact with different systems, and you would receive the haptic feedback whenever you started to manipulate objects that were not real. They were in the actual simulation. So to that level of complexity and engagement these systems provide. Again, backed by our fundamental toolbox add-on, which is Quark, leveraging MATLAB Simulink, as well as QRCP for LabVIEW. So I've talked a lot about these systems, but let's see how they actually work in reality. What are the benefits of open architecture systems? And what I have for you today is actually a multi-arm, multilateral, haptics-based, immersive Tele-robotic systems. A big mouthful, but effectively what it is was Quanser had partnered with the Department of Defense here in Canada and the US, and we worked with them to provide a IED disposal example, meaning there was a test rig that was set up to proof the concepts out in a research environment. And it is quite elaborate, but I would like to illustrate the capabilities that you have when working on Quanser systems. So I'm just going to play this video. So what you're seeing here is a variety of different formats. There's an Omni bundle on the bottom left, which is perfect for introductory robotics and controls. And then you're seeing an individual who's remotely operating these 6 degree of freedom robotic manipulators that were previously supplied by Quanser using our HD Square, which is a haptics device. So utilizing the robotic manipulators and this teleoperation setup, the individual has to, one, locate the IED, remove it, and then also show ability for dexterity to do finite movements. And this is all being controlled remotely and remotely operated. So understanding robotics principles, there's obviously a fundamental mechanical backing, excuse me, when it comes to dynamics and the kinematics of the actual systems, being able to calculate the actual mathematic principles behind a robotic manipulator, such as the Jacobians, D&H tables. That's all fundamentally there for Quanser systems. Where we really strive and the gap that we can fill for you is in the connectivity of the actual systems being open architecture, and by providing you with the third-party support software to connect these systems. So the way we actually go about this, and I'll show you a biomedical example, we have Quark as the underlying software toolchain that adds on to MATLAB Simulink, and it allows you to interface with any language that you like. So MATLAB Simulink, C++, LabVIEW, and we have a stream client that communicates with the server. And that's where we interface with the actual physical hardware to be able to give you the low-level inputs and control of the encoders, the motors, and anything else that you might want to explore. So this example is actually a master-slave, where you have individuals who are using our Denso 6 degree of freedom robotic manipulator, as well as our haptics device, leveraging both the position and velocity control along with measuring force and torque to be able to do laparoscopic surgery. So an individual would be able to come in, they would get trained for surgical applications, and they would be utilizing 2 different HD squares to effectively simulate the act of surgery. And again, this talks or speaks to the connectivity of the overall system. So I'd like to show you the actual granularity that you can get to, or the actual high fidelity approaches that you can take using these systems. Again, there's different descriptions of the overall application in terms of what you might want to do. This is a biomedical application, but the sky's the limit. And the best part about these solutions that are not depicted is the force feedback that you feel. It's very immersive, high fidelity, engaging, interactive solutions that that work right out of the box. They're very, very intuitive to start using. Now, this was a very high level on a robotic manipulation standpoint, and especially with a key focus on network systems and communication. But when you want to touch on communication for robotics in terms of ground manipulation, there are a variety of different solutions around our Qbot2e. And effectively, this was actually from Dr. Tensel. He is actually a researcher, I believe at FSU, so Florida State University, and he developed research alongside his team with a focus on spatially evolving robot formations. So this was a Qbot2e passing through narrow spaces with the presence of an obstacle, and I'll show you one more tier or layer of this. But effectively, his thesis or his approach was the understanding that current distributed control methods have a lack of information exchange to be able to provide spatially evolving multi-agent formations. So let me give you another example of how he's been able to utilize these methods to tackle those problems. So he designed, based on the information exchange that's being received by each of these Qbot2es, a adaptive solution or control problem for situations where agents have control of the resulting formation, meaning each one of these Qbot2es are reading and reacting all at the same time, and they're communicating with one another through a network system. So each can locally store information and has to be able to decipher what the environment looks like around them, and they all have a specific target of following that car. And through his system and his research, he used the Qbot2e to communicate the following medium. But the common sentiment that I get nowadays, and my role at Quanser is the global digital product specialist, through our communications with professors and institutions, the need for improving the engineering experience both on the research and teaching side has become more relevant. And today, now more so than ever because of COVID, but we're looking at the future in terms of how to really expand our capabilities, leveraging online means. And this is an example from Dr. Jinjun Chen, who reached out to us asking for support for this upcoming fall with regards to online labs. So for those of you guys who have ever worked on Quanser experiences, you know and love our reliable, robust hardware and our ability to provide you with real-time control capabilities in an open architecture environment. But now what Quanser has done is we're revolutionizing the way engineering education will be taught, as well as how research will be conducted. And our approach to this is through virtual solutions. We believe that these virtual solutions will be a complete offering for both research and teaching efforts. So imagine taking that Qbot2e or a Q-arm, so a robotic manipulator, or a Cube Servo 2, or finally a Quanser Aero, a twin rotor system, and being able to put that on the desk of every researcher, student, or professor to rapidly design your own controllers or prototype. I have a few examples in terms of how this would look like, and I'd love to really show you what the benefit is from a user standpoint. So you get this interactive, immersive experience that's locally stored on your PC. So if you're a Windows 10 user, you would download this. you can then start leveraging MATLAB Simulink, which you know and love, and replicate the exact parallel experience that you would be working with on physical hardware. The best part about this is, unlike traditional simulation, which is tough to correlate the real world results, you have a physical solution that you can deploy the exact same controller on and see one-to-one paralleled experiences. So right here, you're seeing a visual pick and place of a robotic manipulator called the Q arm. The Quanza arm was launched in March. And this is purpose-built and designed, enabling not just the fundamental robotics curriculum, such as kinematics, dynamics, position control. It also expands on to the understanding of what robotics can be, but now evolving it to incorporate a interdisciplinary approach. So you're seeing an RGBD sensing camera on the top of the arm. You can start to leverage this for a project-based approach for both teaching and effectively research at the highest levels, and I'll explain how that works. But one thing I really want to get across is you have developed this algorithm. You have hardware in a lab, you're limited based on lab time or maybe even infrastructure space. So how can we leverage these solutions at home? Well, you can design a full controller, you can build it 24/7, play with it, tune the actual system, come to the lab setting when you do have that time and deploy it onto the real hardware. Now, when you're looking at these network systems, this is where the true power of Industry 4.0, cyber-physical systems, as well as AI and machine learning come in, because you have smart connected systems that effectively have some type of actuation, some type of sensing, and now you can control the computation aspects of what it's doing. So McMaster has taken this one step further. They've redesigned their first-year engineering program, and McMaster is one of the leading engineering schools here in Canada. They're competing for top spot, but they're innovating using Quanza solutions, both the hardware and the virtualization, to refresh their teaching and research efforts. So I'm going to show you a project-based design approach that they are taking, leveraging a multitude of different Quanza systems in a networked effect. So in this visualization, what you are seeing is actually a project that for undergraduate students are going to be taking on. But I want to open up your creativity as to the world of possibilities that you as a researcher could have. You could design your own network systems, and you can pick and prod into specific aspects of the control theory that you may want to explore, or the robotics theory that you may want to explore. And it really bodes well when it comes to limitations of infrastructure or even hardware procurement, because you can have virtualized duplicates, and you can be testing your algorithms and validate only the portion which you are looking at. So in this system, it's a recycling plant. There's an indexer, so a rotary servo base that deposits the material. The Q arm uses the RGBD sensing camera to locate that object. It manipulates it. It then has to deposit it, call the actual Qbot2e to deposit onto. After it's located the object on the Qbot2e, the Qbot2e then has to sense the actual correct recycling box, if you will, of where it should be deposited. So I'm going to play that back one more time just so you can see it, and I'll let you absorb exactly what just happened. So the next question that I commonly get, especially when working with researchers on their specific papers or on specific theory that they're looking to validate on a physical system is, okay, this is fine and dandy. This is really interesting from a network system. But for me, I am very particular in terms of what my actual research efforts are targeting. I have a specific requirement and I have a specific product in mind. How can you help me? So example of how we've worked with these systems in a physical environment as well as a virtual environment, I can leverage work done by our director of engineering. He calls this a simple lane keeping algorithm, but effectively he's leveraging one of our 1/10 scale model vehicles, which is a fully autonomous vehicle that we've designed at Quanser called the Q car. So he leverages the Q car in his basement to track a line, a yellow line in the center of the road. And his goal is to go as fast as possible with minimal amounts of control on the steering to limit the actual throttle speed. Meaning he's going to be taking very aggressive curves. And as he's taking those curves, he wants to be able to demonstrate the ability to stay as center as possible in the actual obstacle course. So you'll see an example here where he goes full speed around the actual track, and his aim is to keep as centered as possible. But the best part about this is because he's applying this on real physical hardware, there's two things you have to note. One, he needs the physical space, but two, he may not always have access to this area to be able to develop, or it's not always ideal to be developing on the real physical solutions because through any research effort, there's usually an aspect of trial and error and an aspect of rapid prototyping or designing. So what he actually did was he leveraged the Qbot2e virtual environment. And in this environment, he was not limited based on the infrastructure requirements. So he was able to deploy that exact same controller on the Qbot2e. Obviously, with the steering algorithm simplified, he was able to replicate the exact same optimal control to get the Qbot2e to center itself as it was driving around the actual lane. So in summation, I did want to leave you guys off with one last point that these are very new approaches to Quanser. We've adopted times that are changing, but we envision a future where our solutions will be virtualized to allow for every individual to have one of them on their desk and to support the actual development on real physical systems. So in summation, one thing I do need to say is Quanser fully believes in real physical systems. You do need to touch and feel these systems, but this is another approach to provide a one-to-many learning environment, both for teaching and research. And especially in the research realm where you may be limited based on funds or specific concepts you'd like to apply, we're learning that using the software that we've created, it allows you to really rapidly prototype and test your algorithms in a creative, immersive environment. So with that, I'd love to take any questions that you may have. We have a plethora of Quanser support on call. So if you have any specific technical questions, we'd love to delve into it deeper.
Thank you so much for this nice presentation, Tovishan. Guys, please feel free to put your questions on the chat box, or feel free to directly address it to our speaker, Mr. Tovishan. Any questions?
There is a question in the chat, Ralph, the chat window.
Yes, I saw it. So the question is related for the haptic. Is there aerospace application, for example, at the end effector? So Vishan?
I can maybe give an initial response, and I'd welcome any of the other Quanser team to support. My understanding is Quanser systems are open architecture, meaning there's a multitude of different applications that you can create using our systems and add to the actual manipulator. So with regards to an aerospace application, I've seen haptics being applied with a aerospace solution, such as a 3DOF heli. It could be in certain applications, a drone. But to be clear, is the question to add something that has aerospace applications on the end of a robotic manipulator, or the other way around? Like I've heard of drones with robotic manipulation or a robotic manipulator attached to it. I'm not sure, just for clarity, maybe they can expand on that question.
Yeah, Dr. Ghazi, if you can please further elaborate the question. Is that what you mean with the question? And were we able to answer you, or is there anything else that you'd like to ask? He mentioned that he's mainly interested to check the control of the altitude and the angle using the haptic.
For sure, entirely possible, but I will actually invite either Murtaza or Hernando if you guys have any thoughts to maybe add, and maybe even stories of examples of when you've been developing in the back. I know haptics is a loose tie, but perhaps sharing any thoughts from the Q drone.
Hi, this is Murtaza here. So I worked on developing the Q drone system as well as its control architecture. So I have a sense of what you're, I think, talking about. I'm not seeing the relation to haptics directly, but we have cases in which you might want to use the manipulator to interact with the drones, adding disturbances and so forth. Is that something you are trying to get to? Right, so we have those capabilities, whether it is the arms that Provision has shown, or even the Q arm. They have a lot of sensing capabilities on them already. You also have a camera on the Q arm manipulator, so you could do visual servoing to also track the. Oh, great, perfect. Right, so the Q drone, which is now the successor of the Q ball system. It also has a lot more sensors and an onboard PCB that allows you to add way more sensors to it. Similarly, the Q arm, as an example, at the end effector has a PCB, an end effector board that allows you to attach a variety of different tools and electronically attach them to the manipulator and read and interact with them through our software Quark the same way. And this capability allows you now to, for example, add your own gyroscope or accelerometer if you wanted to add to the end effector, or if you wanted to add additional cameras, you wanted to add your own magnetometer. These are all different options to add to the manipulator. And so this way you can interact with all sorts of various systems. All these systems are also connected. So whether it's the Q ball, the Q drone, or a machine that's controlling the Q arm, you can have them do projects together for aerospace applications. Does that answer your question?
Partially. So, is there any further clarification about the question, Dr. Muhammad, that you'd like to ask? Is it something related that that you are interested to kind of superposing a haptic capabilities into an aerospace, maybe into a drone or into a man air vehicle kind of platform? So he mentioned that he's teaching the flight dynamics, and he might be. If you'd like to ask the question directly via your audio, you can unmute yourself also, it's possible.
Okay, yeah, thank you.
Yeah, perfect.
Okay, guys, as I told you, as I mentioned, I'm teaching flight dynamics and also control. So sometimes I would like to explain things to students in flight dynamics, and yeah, I'm concerning applications. As you mentioned in the 6 degrees of freedom haptic, the using them in the Euler angles to show pitch, roll, and yaw. So yeah, I'm asking if I can attach any in at the end effector, anything that measures the torque or the, as you
Oh, I
mentioned.
see. Okay.
So yeah, I can
Right.
use this to, I mean, explain to students or show them some actual like it's like actual visualization, okay, and
Right.
instead of just explaining things on the
Right.
PowerPoint.
So all our manipulators, they actually have current sense, and some of them have torque sensors as well. For example, the Denso. And so if you are, for example, with flight dynamics holding your model airplane wing or a model RC plane or so forth inside a wind tunnel, as that plane is experiencing forces, the using the current sense on your manipulator, you're getting feedback of what exactly those end effector forces are, using the joint torques, and you could use it that way. Um, the the haptics or the HD squared itself, um, the control stick that you use and manipulate around, it moves in 6 degrees of freedom. So that can be connected to other visualizations that allow students to explore what these dimensions are. So, for example, we designed a course for the American University of Sharjah, um, on drone design, and in one of their labs, they work with the IMU that is on board the Q drone, but the motors are turned off, and now they implement their own attitude estimation algorithms to sense the roll, pitch, and yaw state of the Q drone. And once they have done that, they take the actual hardware in their hands, and as they manipulate it around themselves, they can see the corresponding visualization of that drone on their screen, telling them exactly how much the roll, pitch, and yaw, and so forth is. So these systems have a lot of applications beyond the ones that directly come with them. And we are happy to like take this discussion further with you if you're interested in taking a look at how you could incorporate some of these systems into your course.
Yeah, thank you so much. Thank you. I mean, yeah, I'm thinking about this. Thank you so much.
Thank you. I just want to add something about what Murtaza just explained, that our course software also comes with a number of examples from which you can learn how to add sensors to your applications. Either you are using a robotic manipulator or a drone or a Q car, all of them has the capability to add more sensors. And Quanser software also comes with the examples. For example, if you are using a SPI or I2C or any other interface, those examples are beautifully explained in the Quanser software.
Hey, Ralph, I'd like to jump in if you don't mind, and I don't really have access to
sure. Welcome,
my...
Dr. Jamal.
Okay, this has been great, by the way. I attended the yesterday's and today's. And, nowadays, most programs are linked together, interdisciplinary, even at a university setup. And where we are at Prince Mohammed bin Fahd University, we're embarking on starting 2 programs. One is what I call MARS, M-A-R-S, which stands for Mechatronics, Robotics, and Automation. Okay, and I think that fits very well with the way that you presented the platform, and probably multi-use by different even disciplines, electrical and mechanical in particular, by the way, and computer science and others to a certain extent, computer engineering, and biomedical engineering. Those are 2 programs we want to do, and we want to set it in such a way. We do have a center of excellence, by the way, in NI, and thanks to Ralph and company, we have a long-standing relationship. But it is important as a dean, as I want to figure out programs and put assets together to utilize those assets the maximum that I can, jump from one discipline to the other with the new disciplines that you have. A side question that I want to have, you mentioned the modeling, simulation, virtualization, and then of course the ultimate fidelity is to take it into a lab and put hardware together and make your system work perfectly in many different ways. So you take all the iterations and all the things and you put it back into the hardware. Now, you know, most of the students or even researchers nowadays, we do things using probably solid modeling, right? And in those, they can interface and should be. Even for a robotics, if I take it as an example, there are packages like SolidWorks. There are packages like DATS and Atoms, probably working model back in the days, where students can look at even the dynamic side of it, the kinematics, dynamics, force motion analysis. And I think we touched up a lot of the end effector and what goes on in terms of sensing and the feedback that you can get, especially the haptic ones that you talked about. But can you tell me if there is maybe with all these really nice gizmos and gadgets, which we, by the way, we have a lot of Quanser assets too, attached with the NI platforms that we have, is the curriculum, or do you have curriculum specific? You mentioned some courses being developed elsewhere that somebody like me can put even from the design stages of these programs to make sure that these things are embedded in so that we can go into these real great systems together. A long question, but if you can comment, any of the Quanser team, I would appreciate it.
Thank you so much for this great question. I guess the Quanser team will be able to happily address all these challenges.
Hi, this is Murtaza again. So if I'm understanding your question correctly, it was suggesting that I was asking whether or not we have some curriculum that leverages a modern tool chain such as SolidWorks in the curriculum process itself. Is that correct?
Yes, it is. Yes.
Okay. So we directly don't do work with SolidWorks. So what we have instead focused on is saying, okay, the undergraduate level and the graduate level teaching courses, they really focus on either Simulink or LabVIEW. And so we have made that interface with real hardware very simple. In addition, if you bring your own hardware off the shelf, you can connect it to our data acquisition devices and still have a similar experience in that regard. And so from an engineering design perspective, that's what we have directly focused on. Now, if there are software tool chains that you might be interested in having us incorporate into our curriculum, which is, again, freely available, very often professors do come to us and say, I want to use your curriculum with this tool. How do I do that? And we can work with you on a one-on-one basis to figure that out. But in general, we try and maximize our breadth. And so if you've seen that there is a software tool chain being used rapidly by almost everybody, we'll try and incorporate that to make that available based on popular demand. So for example, we've heard about Python again and again, and the Quanser Self-Driving Research Studio, when it was launched, it had full support for ROS Python in addition to Simulink. And that came out of the research community. More and more people are using that nowadays. So if you have a request of that, we are definitely willing to talk about it.
Is that okay with you, Dr. Jamal, or you have some additional information that you'd like some clarification about it? Maybe
I'm fine with it for now, and I think we can pick up on.
Yeah, we can take it offline if you have some particular
communications later on as we design our new programs along with the old ones. Yes, absolutely. But thank you for that answer.
Thank you so much. You are more than welcome. Any other questions? I guess we are running out of questions. We have answered them all. Last chance. Excellent. So, gentlemen, thank you so much. Thank you to Vishan and the Quanser team for addressing this excellent webinar and all the questions of our great partner audience. With this, I would like to enter into the closing of this Q&A session, and we hope that we could cover the majority of those questions and the challenges. And if you have any further please feel free to contact us anytime. Our event reached its end. Thank you for any feedback, and most importantly, thank you for your time. We are very honored to have you in our events, and good luck for tomorrow's events regarding the structural health monitoring as well. And please reach out to us for any further questions. We'll be more than happy to hear your problems and provide you with the right solutions. Have a great day and stay safe.